In this video, we're going to look at the Unit 5, Lesson 8 from Algebra 1, which is on exponential situations as functions. For this first activity, you can shut your book and then just look at the graph on the screen and just think about a couple of things that you notice and wonder about the graph to prepare yourself for the lesson. So just what do you notice? What do you wonder? Could have noticed anything, right? And wondered anything. So maybe you're just noticing that there's, a graph that seems to only be going upward, right? So we only see these increases and it stays flat for a while and then it'll go up again and be flat and then go up again. Maybe you noticed the horizontal axis has the numbers 0 to 60. The vertical axis has 0 to 1.6. So it's only counting by 0.2s. Versus the horizontal seems to be counting by tens, and then it's got the little dashes in between to count by twos. Anything you noticed, anything you wondered is great for that. So then what we want to think about is use your graph to support your answers to the following questions. Is the accumulated rainfall a function of time and vice versa? So is our rainfall, which is our vertical axis, a function of time, which is our horizontal axis, and then vice versa, is time a function of rainfall? So think about those answers for a second. So when we're talking about whether or not something is a function, it means that it means this of the function needs to produce only, each value needs to have only one specific output. So you can't have two of the input values that go to different outputs. So as we're looking along these values of time here, when we go up to the graph, it can only go to 1 point. Okay, so at 10, it's going to 0. At 8, it's going to 0. At 12, it's going here. At 14, it's going here. 16, 20, 30, 40, 50. It's going to these one specific outputs. Okay, it's never going to two different places at the same time. So then this would mean that, yes, this is a function. So the rainfall, there's one specific rainfall amount at each day. Then when we look to switch this around, so is time a function of accumulated rainfall? So now this is our input. Does each rainfall amount happen at only one time value? Okay, does each rainfall amount happen at one time value? And we can see that that's not true, because if we do this as the rainfall and this as the time, we can see at 0 rainfall, okay, that's happening at a time of 2 days. We have 0 rainfall at 4 days. We have 0 rainfall at 6 days. We have 0 rainfall at 10 days, 8 days. Okay, so all of these have 0 rainfall. And so we do not have one specific time value for each rain value. And you can see that happening in other places too, right? So like this chunk of time would be repeats, or this chunk of rain would be repeats. So at 0.9 is happening from about 24 days to 40. So that would be another problem. But so time is not a function of rainfall. Rainfall is definitely a function of time, but time not a function of rainfall. So we talked about this. Why is the rain a function of time and why isn't time a function of rain? Now let's come up with a few other statements that are examples of a function and then use function notation for these. So let's just use function notation. So if we're saying that rain is a function of time, we could write that like this. So we could look at a rain value. So we want to come up with the rain after 6 days. And this from our output. So what was R of 6? So here's 6 days. The output is 0 inches of rainfall. So this would be, there is 0 inches of rainfall after 6 days. So that's how we would say that as a statement, and then there's the function notation for it. We could look at other things. So we could say after 60 days, there is, and now we have to go look at the graph. So after 60 days, there is like 1.4 something inches. So after 60 days, there is 1.42 inches of rain. And then in function notation, right, that would be R of the time period. So the function at 60 days, the rainfall at 60 days is 1.42 inches. Okay, then this next activity, you are going to create a table, equation, and graph for a scenario. If you have a partner, you'll discuss why or why not the relationship is a function. Otherwise, think about it on your own. And then discuss the potential domain values that would make sense for the scenario. So our scenario is that Claire noticed mold on the last slice of bread in a plastic bag. The area covered by the mold was about 1 square millimeter. She left the bread alone to see how the mold would grow, and the next day, the area covered by the mold had doubled and then doubled again the day after. So we've got this 1 square millimeter is the start that she noticed. And then after one day, the area had doubled, and after another day, it doubled again. So there's some questions in your book to answer about this. So why don't you pause the video, answer those questions, and then come back. All right, so number 1 said if the doubling pattern continues, how many square millimeters will cover the mold 4 days after she noticed, right? So the first day she noticed there was 1 square millimeter. Then this is going to double that first day after she noticed. So 1 times 2 is 2. Then the next day it's going to double again, and 2 times 2 is 4. Then it's going to double again after 3 days, and that will give us 8. And then it'll double again after 4 days, and that will give us 16. So 4 days after she noticed, she'll have 16 square millimeters of mold on that bread. So number 2 asks us to represent the relationship between the area in square millimeters covered by the mold after D days. And it wants us to do a table of values, an equation, and then also graph it. So your input is D, like it asked, and then your output is the area of the mold. And so you can just plug in a couple of values here. So the day that she noticed is going to be day 0. That was at 1. Then we already did these after 1 day, 2 day, 3 day, 4 day, and let's just add in maybe a 5th day here. So after 1 day, it had doubled to 2. After 2 days, it had doubled to 4. 3 had doubled to 8. 4 had doubled to 16. And then after 5, it would double to 32. And this would, this told us just to go through 5 days. So now if we write an equation for this, okay, so our function notation is going to be area as a function of days. Our initial value, so remember you start an exponential function with the initial value, and that's what's happening here at 0 days, okay? So we're looking in here, the output. So here's your initial value. That's going to start your equation. And then we multiply by the growth factor. Okay, so the growth factor is how much is it changing over each equivalent ratio of time. So what's it multiplying by? And so remember, we knew that this was multiplying by 2 each time. So that's our growth factor. And then our variable is an exponent here since it's repeat multiplication. So our equation would be the area as a function of days is equal to 1 times 2 to the d power. Then it asks you to graph it, so we can just draw a sketch of this graph. So 1, 2, 3, 4, 5. So I'll count by ones here, and then we need to get up to 32. So I'll do 5, 10, 15, 20, 25, 30, and then 35, I suppose, so we can get all the way up there. So these are counting by fives. So at 0, it was at 1. At 1 day, it was at 2. At 2 days, it was at 4, and you're drawing a sketch here. At 3 days, it was at 8. At 4 days, it was at 16. And at 5 days, it was at 32. And if you wanted to connect these, I suppose you could. But these are just our dots from each day. So we'll talk about the rest of that in a little bit here. So those are 5 data points. Then number 3 says, discuss with your partner is the relationship between the area covered by the mold and the number of days a function of time. If so, write what is a function of what. If not, explain why not. And so we saw in our table that all these inputs only had one specific output, and each day it's going to be growing more, right? So it's going to keep getting different values there. So this would be a function of time, okay? So if so, write what is a function of time. So area is a function of days would be true. So this is true. Okay, so yes, it is a function because each area comes from a specific day. So can the independent variable here, which in this case is the number of days, be something like 1.5? So when I talked about connecting it, like could we have non-whole number values? Why or why not? And is there an area associated with 1.5 days? So, you know, you're looking at it each day, but this would be after 1.5 days. So this would be like 12 hours into the next day. So the mold doesn't just, you know, when you looked at it at 6 a.m., it was this big, and then it does nothing until the following day when it's this big. Right? It grows slowly over time throughout those days. So if you looked at it after 1.5 days, you would see that it had grown. It wouldn't have doubled yet because it's doubling every 24 hours or 1 day, but certainly there would be area associated with that 1.5 day. So what would the meaning of a point on the graph where the value of D is, for instance, between 2 and 3? So like if we're going back to this graph that I had drawn here, and if I connected this, right, what would the value between 2 and 3? So here's 1, 2, 3. So we're looking in between these two. What would the value right here represent? Well, it would represent that growth of the mold between day 2 and 3. So somewhere on day 2 before day 3. So, you know, 2 days is what, 24 hours and 36 hours. So if we looked at this in hours instead of days, it would be somewhere between 24 and 36 hours. And then what domain would be appropriate? Can the mold grow indefinitely? Why or why not? So it certainly is going to continue growing, right? So an appropriate domain would be from 0, okay, because we started at day 0, right? And then our domain is days. So remember that our domain is our independent variable, in this case, days. So starting at 0 until something. So far we're at 32 days, and that's giving us 32 square centimeters of space. So it really depends on how big this slice of bread is, because the bread is going to matter. Okay, so if we go 0 to 5 days, remember that this output here that we got here was 32 square centimeters. So it really matters how big is a slice of bread. So the domain would be until the whole bread got covered, because it can't grow indefinitely. So this indefinitely is, it can only grow, I'm going to do a different color so you can read this. So can only grow to the size of the bread. And by size, meaning area of the bread, right? So area of the bread. So however big that is, then those days would be your input. So if a piece of bread is 32 square centimeters, then 0 to 5 seems to make sense. Okay, if it's more than 32 centimeters squared, it can continue growing for that. And I would say all numbers between those. Okay, so meaning decimals are fine. Okay, so 1.25, 1.1, 2.7, 4.8. Okay, everything between that. So then here's some vocab that you can write down in your book. You can put it at the end of your lesson here in your book. There's probably a spot on your summary for this. Otherwise, wherever you write down vocab is fine. But an exponential function is a function that has a constant growth factor. So another way to say this is that it grows by equal factors over time. And remember that factors, okay, so this word factor means multiplication. Okay, so you're seeing it double, multiply by 2 every time, multiply by 3, multiply by 1.7, but it's got repeat multiplication. For example, f of x equals 2 times 3 to the x defines an exponential function. Anytime x increases by 1, f of x increases by 3, because remember that this base of your exponent is your growth factor. And then that number out front is your initial value. Okay, so then if there's a number here, it could be a 1, in which case it might not be written, but then that's your initial value, or the starting size of whatever function you're looking at. Okay, for this next activity, we're going to revisit some exponential relationships that we've already worked with and then express them using function, language, and notation. So you're going to be writing a sentence and then identifying and using the independent and dependent variables to write an equation. And then you're going to share your reasoning. Okay, so we're going to look at a couple situations, like I said, and this is what you're going to do. So I have this on every screen. So you're going to write a sentence in the form of what is a function of what? Okay, so is in the last case, we had area is a function of time. Okay, in that first problem, we had rainfall is a function of time. You're going to indicate the independent variable and the dependent variable. So which one is going in and which one is coming out. So which one is it a function of? So this would be the dependent and this would be the independent. And then you're going to write an equation. Okay, so for each situation, so you can look in your book at these and try this out and then come back to the video. So I'll just pause the screen. You can just pause the screen like this. So you have the instructions on the screen. Go to those 3 situations and then come back. Okay, so for the first one, we have in a biology lab, a population of 50 bacteria reproduced by splitting every hour on the hour. The bacteria splits into 2 bacteria. Okay, so here's our initial value and here's our growth factor, right? So another way to say this is doubling or multiply by 2. Okay, so that's our growth factor. And so first it wants us to write a sentence in the form of what is a function of what. So in this case, we have the number of bacteria is a function of time or hours. Okay, so the number of, and this is for our first bullet point, the number of bacteria is a function of hours. Okay, the time that's passed in hours. Independent variable would be the number of hours, the time that's passed, because as the time changes, the number of bacteria gets more. So it's that time, that's the independent variable. And then the dependent variable is the number of bacteria. And then if we want to write an equation, so we have bacteria is a function of hours. So I'll just call the function B and then the input H. And you're going to do your initial value. So remember that's 50 times your growth factor. In this case, it's doubling. And then raised to a power of the independent variable, which in this case is hours. So I'll just use H. Remember that this input variable needs to match the variable that you have in your function. So 50 bacteria to start, and they're doubling each hour. Next situation, every year after a new car is purchased, it loses 13% of its, oh, this should not be 13. This should be 1/3. 1/3 of its value. So let's say that the new car costs $18,000. Okay. So in this case, we have the value of the car is a function of years, right? So it said the year since purchased. Okay. So the value of the car is a function of years since it was purchased. Then indicate the independent and the dependent variable. So the independent variable here is the number of years, and the dependent variable is the value of the car or how much it's worth. So then the equation, so we've got the value of the car since the year's purchase. So I'll just use V for my function and Y for my time. Now, the initial cost of the car was $18,000, so that's our initial value. And then we're going to multiply that by the growth factor. Now, this one's a little bit interesting because it's losing 1/3 of its value. So we want to know how much value it's retaining. So this is what it's losing. So what's it retaining or keeping? So if it's losing 1/3, it's keeping 2/3. So it loses 1/3 of its value. It keeps 2/3. So this is going to be your growth factor. Okay, so it keeps 2/3 of the value. And then this is per year. So then Y as the exponent there. And then third one, in order to control an algae bloom in a lake, scientists introduced some treatment products. The day the treatment began, the area covered by the algae is 240 square yards. Each day since the treatment began, 1/3 of the previous day's area. So this is like the last one, right? So 1/3 of the previous day's area. Oh, it remains. So this one's a little bit different. So this is how much remains. So it's not losing 1/3, it's remaining. So 1/3 is remaining covered by algae. So when we write a sentence and when we write our sentence, okay, it's going to be the area covered by algae is a function of days. and it's days since treatment was introduced. Okay, so then the independent variable is the days, and the dependent variable is the algae area, right? And then if we go ahead and write our function, okay, so this time we have area covered by algae after a certain number of days. The initial value of your area of the algae was 240. And now this time the growth factor is 1/3 because it says a third remains, and we're writing how much is still there. So we want to use how much remains. And in this case, it's 1/3. And then we have after D days, right? So then D will be our exponent. So careful on that remains versus loses. All right, so then you can just talk to your neighbors about the variables and the units of the variable. I already went over them, but if you want to see if anybody used any different variables in your class, you're welcome to ask them that. Okay, so here's the lesson synthesis. So let's discuss. So consider a bacteria population described by the equation P equals 1,000 times 2 to the T, where T is the number of hours after it's first measured. Complete this sentence for the situation. So what is a function of what? So we'd have the bacteria population is a function of the number of hours since it was first measured. So then these questions, so how is P, which was from our situation, right? So how is P related to the function F given by this? So our population is equal to that function, right? So those functions, that function is the same as this one. Whoops, which you can't see me circling. So it's the same as this one, right? So those are the same. So P is equal to F of T. So how are these equations alike or different from what you've written previously without function notation? So they express the relationships in the same way, but both equations can be used to produce a table or a graph or answer questions about the bacteria population. So the notation P equals F of T just makes it explicit that P depends on T. And then how are the exponential functions here like or different from linear functions we saw earlier in the course? So both, relate one quantity to the next, but linear is repeated adding or subtracting versus our exponential functions are repeated multiplying, and really multiplying or dividing. Okay, but a repeated factor versus a repeated difference. So here is the lesson targets for today. So can you use function notation to write equations that represent exponential relationships? And when you see relationships in descriptions, tables, and equations or graphs, can you determine whether the relationships are functions? So those were the goals for today. You can work on check your understanding by doing your lesson 8 practice problems in the pages after this in your book. You can also try this cool down to see how you're doing. And if you have questions on it, be sure that you ask your teacher.